I didn't record fourth period, so I figured I'd record this one. We're going to talk today very much about the things that I'm going to expect you to be able to do that are related to work and energy. And in order to do that, I want to kind of start by kind of picking up right where we left off yesterday, which is giving you kind of a quick overview of all the things we've put together. So first, can't throw out this idea that we have this basic building block of energy. When I say basic building block, this is the most basic kind of energy that there is, the energy of motion. And it's easy to understand this kind of energy because when we look at our stuff, you know, if it's moving, it's got this energy. That's great. We added to this, though, this other kind of thing. We've talked about work done on a spring. And although I didn't make it clear yesterday, and I mean, if I did, I'd say clear as mud would probably be the right way to say it. What I did do is I did indicate that there is this thing to worry about when it comes to positive and negative, when it comes to work. And specifically, the work done in compressing a spring relative to the spring is negative 1/2 kx squared. And what this indicates is that this is the amount of work you're going to lose that's going to be stored in the spring while compressing a spring. So Kyle's really just got us, you know, as like background music in his car while he's driving his dog somewhere. I don't want you handling the phone while you're driving. You focus. But I don't think he's going to learn anything today. But at least I'm going to say he's here, but yeah, I don't think we can count on him learning anything. He's probably on his way to the beach with this cat dog. It's not a dog. It's not a cat. I don't know what it is. You know, there was a cartoon on Nickelodeon called Cat Dog. Yeah. All right. So the last thing I want to throw out here too is there is the idea that net work can change something's kinetic energy. But in addition to this, we know that net work and work aren't the same thing. There's work done by an individual force, but there's net work, which is the sum of all the work done on an object from multiple forces. This one word, net, is I mean, it's tiny, 3 letters. Pay attention to it. It changes the whole meaning of what it is that you're working on. So when they ask for something net, they're talking about the sum, the result, what happens when everything's there. So net force, net work, they are clearly different things. And you need to pay attention to when that word is being used. But let me talk about this for just a moment before we really go into what I want to talk about today. And I need to give you this reminder that it comes from Hooke's law. And Hooke's law has this explicit negative sign. And I hate to be a person just sits there and harps on what these negative signs mean. But in this case, the negative sign has some interesting and critical meaning. First, it means that this is a restoring force, which means that the force that acts from a spring acts to restore the object to its original shape. Now, any system that has a restoring force has a force that's going to attempt to return the object to its original shape. So it doesn't have to be a Hooke's law, but the word restore means just that, to restore it to its original position or original shape. So I want to kind of give you an idea of what it means to have one versus the other. Like, what does it mean if you don't have a restoring force, if that negative sign isn't there? So I want you to imagine a bowl. If I have a bowl and I put a marble at the bottom of it, the marble is located currently at the equilibrium position, which means that it's at 0. If I displace the marble a small amount in the bowl here and release it, there's going to be a force that's going to act to return the marble back to equilibrium. Now, it might not stay at equilibrium. It might oscillate back and forth inside the bottom of the bowl. But the idea here is that displacing it creates this force at the instant you displace it that attempts to return the system back to equilibrium. That's what that negative sign means, that the displacement in any direction immediately creates a force in opposition to the displacement that's going to attempt to return the system back to the way it was, which is the opposite of what would happen if I took that same bowl and turned it the other way. Ooh, that's not what it looks like the other way. Let's try that again. Better-ish. We're going to go with that. That's my story. If I take the bowl and turn it upside down, I could still probably perch the marble right there at the very top at equilibrium. And if I'm really careful, it'll probably stay there. But if I was to displace the marble a small amount, is there any chance it's going to return back to equilibrium? No, because that would be what would happen if there's a plus sign in Hooke's law. A small displacement creates a condition for a continuous displacement that will disrupt the system, that will throw the object away. We want our buildings to be like this. If the wind hits our building and displaces the building, we want there to be a restoring force that's going to attempt to return the building back to its original position. We don't want to build our buildings like this. And I know that you're kind of, Mr. Shelton, you're just kind of generalizing. No, we test buildings and we look for oscillations and we look for situations in which the things that we have built might have forces that we weren't prepared for that act to disrupt the system in a manner that would have a plus sign there as opposed to a minus sign. We are almost always hoping that our structures return to an equilibrium position, that they're constructed in such a way that small displacements don't destroy the system. So I don't want to minimize it, but I want you to understand that that minus sign, although has implications here, it has implications in a lot of space. So this is what I mean by the difference between one restoring force versus a non-restoring force. So this was the kind of the big takeaway from earlier. So what I want to talk to you about today are first two things. I want to talk a little bit about potential energy today and how it relates to work done against a conservative force. And second, I want to show you an example of what kind of the level of expectation is going to be for the problems we're going to have to do. So the first thing I want to do is I want to throw us back to where we talked yesterday, that if we have a spring, that's my spring, and we attempt to place a box like here next to the spring, we'll say that this is equilibrium, that displacing the spring, meaning taking my box and applying a force in such a way that it compresses the spring, like so. Like that. So here we've taken and we've moved the spring back a distance X, and therefore work was done by the spring in being compressed backwards. Now, the work has to be negative because the force from the spring was to the left, but we displaced the system to the right. So negative work had to be done by the spring on the box. Now, it's not a surprise that something had to lose energy in order to compress the spring, but there is something that is unique here. If I release the box, the restoring force is going to do positive work back on the box. And that work could go to changing the kinetic energy of the box. Meaning when I compressed the spring, I probably did so in such a way that when I let go, if I was holding the box here, the box would stay indefinitely there. Like maybe I have a latch that I could put here, just hold the box in place. The force I applied to the box did work in compressing the spring that is now stored in the spring, which can be returned back to the system when the spring is allowed to expand and push again on the box. That would be net work on the box and would go towards changing the box's kinetic energy. This relationship between the box and the spring is an important one and is considered a manner in which energy can be stored. We say that this relationship represents a conservative force, and conservative forces can store energy indefinitely. So we define potential energy as the amount of work done against a conservative force. And we put a negative sign there to indicate that the energy is now stored in the system, meaning doing work against a conservative force provides negative work against that force, but we say creates a stored amount of positive potential energy. Now, it's hard to understand why this negative sign and why this formality has to be here. And it won't be clear right away. But what I have to have you understand is energy had to be taken from someplace else and placed inside this system. So no matter what, the environment lost energy in compressing the spring so that the spring could store that energy. When released, that energy could be returned back to the environment. But for right now, it's stored inside the spring mass system. The thing about systems is that systems don't act on their own. A system is an interaction between two or more objects. So the spring doesn't store the energy by itself. The spring stores the energy because there's something affixed to the spring on one end and something else that's applying pressure on the other. Without both of these, no energy can be stored in the spring, meaning if this wasn't here and I attempt to push on the box, I won't store any energy in the spring. The spring requires a system. It requires that there be a part of the environment where the spring interacts with that environment. Now, if that doesn't make a lot of sense right now, maybe this will help. Consider this arrangement. I want to lift a box a distance h. Okay, so I'm going to lift the box a distance h. To lift the box, I apply a force on the box upwards. The amount of work I do on the box, so it's the work by me on the box, will be the size of the force I apply times the cosine, 0 degrees. I'm going to push up on the box, and the box is going to go up, times h, the displacement of the box. Now, at the same time, there's another force acting on the box. Now, I'm pretty sure that this force, if the box does go up, the force of gravity is either less than or equal to my applied force. Does that make sense? Meaning I couldn't lift the box unless I at least push up on the box with enough force to equal the weight. I could push more than that, though. But the work done by gravity is going to be mg times the cosine of 180 degrees, right? Because gravity is acting down, but the box is going up, times h. Now, by definition, cosine of 180 degrees is going to be negative. Let me move all this stuff over here for just a minute so I can write to the side. Meaning there's the work done by my upward force, which is going to be F times h. There's going to be the work done by gravity during the same time, which is going to be equal to negative mgh, which is going to produce a net work of FH minus mgh. Now, if I push up harder than the box's weight, then this is going to be equal to the change in kinetic energy of the box. Meaning that when we get here, although the box is above the ground, it might also now be moving with a new velocity due to the fact that it was accelerated upwards. But how much extra kinetic energy it has to be the difference between the amount of energy I gave the box and the amount of energy that gravity took away, that gravity prevented from the box acquiring as kinetic energy. But, and here's the thing, the box is now above the ground. What I mean is, although gravity worked against me lifting the box, if I drop the box from right here, I'm going to get back this energy as gravity does work on the box, bringing it down. So unlike friction, which would do work and take the energy away from the system forever, in a situation like this, gravity does negative work in a way that is reciprocal to the environment, meaning I could get this energy back. I mean, imagine if these two forces were equal. If these two forces were equal, then when I added them together here, the total would have been 0, meaning I would have reached H and the box could stop right there, or there'd be no change in kinetic energy right there. But if I were to immediately let go of the box, suddenly gravity would bring the box back down with the same amount of energy that it took away on the way up. This would change the kinetic energy of the box, and therefore when the box made it back to the ground, it would be zooming because it would have that kinetic energy. The reason I'm bringing it up like this is when we talk about the interaction of the box in our environment, we need to be cautious of where the energy is going in our environment. At the same time, doing work against a conservative force like this does store that energy in a way that we can get that energy back in the future. In this case, we'd call this gravitational potential energy. Potential energies are forms of energy where we are able to get a reciprocal one-for-one return on the amount of stored energy. There's not many forms of potential energy out there that allow us to have 100% return on the energy storage. In fact, it only works for certain types of conservative forces. So all of the fundamental forces work in this way. So there is definitely going to be electrical potential energy storage because the electrical force is a fundamental force. There's definitely gravitational potential energy, which we'll see in two different ways. One for situations like this near the surface of the Earth. And then second semester, we'll see situations where we're dealing with, this energy storage between like heavenly bodies, planets, stars, moons. But there's also other forms of restoring force that exist. The spring is a good example of that. The spring is considered elastic potential energy, and the amount of energy storage is based on the elasticity of the spring. But again, we'd call this elastic potential energy. The one thing that I need you to understand when it comes to all forms of potential energy is that the energy is stored in the interaction between the object and the force. So here, the energy is stored in, when it comes to gravitational potential energy, this is an interaction between the object, the earth, and the force between them. The more we attempt to separate the objects, the more energy that gets stored. On the spring, it's the interaction between the object and the spring and whatever is holding the spring in place. So all forms of potential energy require an interaction. And usually all forms of potential energy require more than one object. So what I'd like you to see is an example of how we might turn this into a problem, into something that you would have to study and discuss. And so here's an example of a AP style question that's based on this discussion topic. And it has a spring that is long enough to have a measurable distance away from the ground. Sorry to bore you. We'll just mute that right there. We're going to place a box and say that work has already been done on the box to take it to this location. All right. So a couple of things. First, I want you to consider point A for a few seconds. I don't think this is hard to do, but I want you to kind of see, could you come up with an expression for the change in kinetic energy of the box due to gravity if it was released from H2, but before it started compressing the spring? This shouldn't be too hard. So give it a second, but let it sink in. I want to figure out how much work would be done on the box by gravity and bring it from its current position to a position just before it starts compressing the spring. Hopefully that won't be too hard. So this is the work done by gravity. It's going to equal the size of that force, mg, times the cosine of 0 degrees, because in this case, gravity is acting downwards. The box is going to go downwards, times, well, this is going to be the hard part, the displacement of the box from where it is to the top of the spring will be h2 minus h1. This is going to be non-zero, so there will be a net amount of work done on the box, and this would end up being the kinetic energy of the box. But now consider this situation where the box has compressed the spring. Say a distance x. In discussing the compression of the spring, can you come up with a relationship that would allow us to determine how far the spring was compressed? Everybody got what they think is their response? What I'd hope you would see here is that the net work done on the box is 0. The object's velocity here was 0. The object's velocity here is 0. So the change in kinetic energy of the box is 0. The work done by the spring is pretty easy. You don't have to do the calculus. It's -1/2 k x squared. That's the work done on the spring by the box. It's negative because it compressed the spring. And more importantly, it's negative because the force from the spring was upwards, but the box was displaced downwards. So the work had to be negative there. But the work done by gravity is definitely positive. The downward force of gravity was mg the entire time. It was in the direction of the displacement, which was downwards the entire time. But the box traveled a distance of h2 minus h1 still, plus an additional distance x. Right, from here to here is still h2 minus h1. Don't lose sight of that. But gravity was still acting while the spring was being compressed downwards. The total displacement is from here to here, and that has to be this displacement. And when I add these up, they have to equal 0, because the change in kinetic energy of the box is 0 from the initial condition to the final condition. Doesn't matter that it picked up speed in between. The network formula doesn't say that this is distance dependent or this is the path dependent. It's just the absolute change in kinetic energy from the total amount of work done. So consider this. You might not see what I'm trying to get you to see because I'm purposely making it cloudy. But if you look at the part of this problem I asked about, how far is the spring compressed? It should be clear to you that this is a quadratic. That there's potentially two places, which shouldn't make any sense. Because I'm pretty sure the box never stopped anytime before the spring was all the way compressed. So why is there two values for x? Anybody have an idea?
Could that represent before you drop the box?
That would be a good guess, but that's not actually it because there is no x before I drop the box. But keep going.
Can I say it?
Yeah, I'm looking forward to it.
Okay. So once the spring decompresses, it's going to pass equilibrium again, and then it's going to be pulling the box back downward if they're stuck together.
That's right. If the box were to stick to the spring, the box would oscillate back and forth, reaching another place over here where it might stop. This is anticipating the fact that there is another place where it could return to a point where the box's velocity was 0. It gives us both positions because there is a future position where the spring is extended, doing work downwards, bringing the box back to rest. Of course, the box would have to stick to the spring for that to happen, but this function doesn't know that. So yes, that's the first thing I want you to recognize, is that it's a little bit different than what we would talk about last year. But also, I'm going to ask this question, but I want my answer to be put in the participant window. I want you to look closely at this, and I want to get some of this distraction away that I have drawn on here. And I'll call your attention back to that point A again. When I drop the box, is point A where the box will be going the fastest? If you think so, put yes in the participant window. If you think not, put no in the participant window. All right. I'm looking at that thing. I got 14-2. And 14 of you say yes. So let's see who my no's are. I got Max and Ryan. So Ryan, why do you say no?
I think that once it hits the spring, the acceleration is going to decrease, but it's not going to instantly become a negative acceleration.
Perfect. That's exactly what I was hoping you'd say. And guys, this is something that I'm not trying to trick you, but it's one of those things where you are easily tricked. And this shows up on the exam frequently. When the box makes it to here, at that moment, is the spring compressed yet? At this instant, there's just one force acting on the box still, and that's gravity, and that's downwards. So it's still accelerating. It's still got an unbalanced force downwards that's causing it to speed up. Now, the box might begin to compress the spring sometime after this, sure. And at that time, the spring's going to start getting compressed. But there's still going to be a time when the upward force from the spring, Kx, is not matched by the downward force of gravity, which means it's still accelerating. It's still getting faster downwards. We don't reach a point where it's no longer accelerating until it has compressed the spring enough for the downward force of gravity to be equal to the upward force of the spring. At that point, it's still moving downwards. It's just no longer going faster downwards. It's starting to slow down, which means we can't get away from observing acceleration. Acceleration is still a part of this problem, and it's still accelerating. Energy can't tell us that, meaning energy can't tell us when it's no longer accelerating. I told you that from the beginning. Energy is really good at velocity. It's really good at position. It's really bad with acceleration and time. So if I want to find out where the object is no longer accelerating, I have to go back to use force for that. Now, once I find this location, and this location tells me exactly where that point is, then I could go back and figure out what its speed is at that moment. But until then, we still have to remember you are easily tricked. Now, I'm going to stop here because we've done this whole problem in talking about work and the concept of net work. This isn't conservation of energy yet, but as most of you know from working last year, conservation of energy is a concept that makes this go by a lot faster. This idea that we have to continue to look at the work happening in our system is nice and serves us, but conservation of energy will create the ability to look at a problem in a much more particular and I think faster manner. Now, I'm going to be posting an FRQ. It is not due on Monday, but it's an FRQ that is this problem as it is on an actual AP exam from a couple years ago. Look at the way in which they ask the question and the types of things that they ask. You guys who are just coming to this material for the first time, look at the homework, focus on the homework in the book, get comfortable with the terms. You guys who have done this before and the homework is probably way beneath you, please look at the FRQ. Take a look at it, run through it, see what level of difficulty it feels like. All right? But this is where I'm going to end for today, unless you guys have a question. Look, I appreciate you guys hanging out. I appreciate you coming today. I know this is not what you would like to do. It is beautiful outside. It's still early. Go do something fun. Start your weekend. Enjoy yourselves, okay? And look, we are on target. There will be nothing for you to do over Thanksgiving. We're going to finish on Friday, walk away, leave all your books wherever they are, and don't even look at them again until you come back after Thanksgiving. We're going to make that happen this week. Okay, guys? All right. It's been good to see you. Enjoy your weekend.
Have a good weekend.
Mr.
You too.
Mr.
Bye-bye,
Shelton.
guys. Bye-bye.